Hello everybody! In this video we're going to talk about how to derive the kinematic equations using basic calculus. In doing so, we're going to talk about 4 different cases that are common in kinematics questions, and by evaluating those cases it's going to become fairly clear where the kinematic equations come from, or at least in theory. So let's talk about case number 1. Case number 1 the story for case number 1 could be told by any Calculus 1 student. It's pretty straightforward, and that is when position is given as a function of time. So we can call that s of t. So if we have position, we can find the velocity like such, and if we have the velocity, we can find the acceleration like such. So pretty straightforward, pretty fundamental, and pretty simple. Case 2 is, what if we have the velocity as a function of time, aka v of t? How would we find position and acceleration? Well, using the same equation as in case 1, we can say v equals ds dt. By multiplying the dt over to the other side, we can say that ds is equal to v dt, like such. Then we can say s final minus s initial is equal to v dt, like so. Then we can say the acceleration is given by the same equation as above. If we're given v, of course, we can just use this equation here to find a. So those are the first 2 cases. And then case 3, I think things will start getting a little bit more interesting. So case 3. Case 3 says, what if we are given acceleration as a function of time, or a of t? Well, using the equations above, we can say that a equals dv dt, and we can say that v equals ds dt. Well, using the same tactic as above, we can multiply a by dt, and we will get v final minus v initial is equal to the integral of a dt. Now, if we were to make a constant, assume that a is constant, we could bring a outside of the integral. Doing so would give us something that looks like this, equals a, and then if we took the integral of just plain old dt, what do we get? Well, by taking the integral of dt, we just get t. So we can now say that velocity final is equal to at plus vi. It's a pretty familiar looking equation, I would say. So then we can do something else, something a little bit different. So earlier in the previous part, we said that s final minus s initial is equal to the integral of v dt. Well, if we plug in v that we previously found by assuming that a is a constant into this equation here, into that v, we'll obtain the following. S of s minus f of I equals the integral of at plus vi dt. All right, taking the integral of that and assuming that a remains a constant, we'll get s of f minus si, so s final, or position final, minus position initial is equal to vi I times t plus 1/2 a t squared. And that is usually the way that kinematic equation is written. And likewise, this is often the way that this kinematic equation is written. All right, so one more case, case 4, and I think that might unveil a little bit more for us. So case 4, and that case says, what if acceleration is given, but this time it's given as a function of position? So acceleration as a function of position, or a of s, we'll call it. All right, so we can begin by writing this equation here. So acceleration equals dv dt. All right, that's well and good. But we can also say that is equal to dv ds, right? Because we're trying to make it in terms of position. So what do we need to multiply that to make that true? Well, to make that true, we need to get rid of the ds, so we could put ds up here, and we'd have to put a dt down here. So now that statement is true. Well, we know that this term right here is just a fancy way of writing v, right? So I could rewrite all of that as dv dt is equal to v dv ds. And this is probably one of the most unintuitive ways to write this, or I guess most unintuitive thing in this video thus far. But this does propose some pretty cool stuff. So, and we just said, or up here, that equals a. So now I can say that a equals v dv ds. So if we multiply that ds over, and I'll move up here, right? If we multiply that ds over, we get a ds equals v dv. And if I were to take an integral of both sides, what would I get? Well, on this side, I'd get 1/2 v final, right, squared, minus 1/2 v initial squared. And I could say that is equal to a ds. And if we're assuming that a is a constant, and only if a is a constant, then I'm able to say that a s minus s initial, or s final minus s initial. And I believe that's the most typical way that last kinematic equation is written. Sometimes they'll distribute it out, but that's generally how it's done. So if acceleration is constant, you're able to use the 3 kinematic equations that I've outlined. And if it's not constant, then, well, you can just resort back to, whoopsie daisy, you can just resort back to their previous state in integral form. But obviously, those can't be presented to high schoolers who haven't yet taken calculus, or perhaps are in the midst of taking calculus. Well, there you have it, y'all. So we have 3 different cases: position time, velocity time, acceleration time, and then acceleration position. All not too difficult, very useful formulas. They don't take too long to derive, but if you're in a position where you are able to learn them, you do have the math background to learn them, I would suggest learning them over memorizing them. Memorizing them is just one more thing you're going to forget whenever you need it, right? So I hope this helped, and I will see y'all in the next one, if y'all are ever so lucky.